We're still talking about bonding. I do mean chemical bonding. We started off bonding ionic compounds. That's really the simplest place to begin. You get a complete transfer of electrons from one atom to another and you make ions. And then the attraction is electrostatic. But we sort of dipped our toes into the covalent pool. And now we're going to jump in head first. We're going to look at the covalent bond itself. We're going to deal with Lewis structures again in more detail and use them in covalent situations. Then we're going to, let's see, eventually we're going to get down to the geometry of molecules, because that has a bearing on whether a molecule is polar or nonpolar. That is, does it exhibit a partial, even though it's covalently bound and they're sharing electrons, does it exhibit slight redistribution of electron density, which makes for an uneven charge? So that's where we go with polarity. All right. Now, a review. Covalent bonds, ionic bonds, are always between a metal and a nonmetal. That's pretty straightforward. But as they get closer together on the periodic table, your nonmetals over here and your metals over here, as they get closer together, the ionic character seems to become less important. And now we're shifting closer and closer to covalent character. So all bonds have an ionic character. All bonds have a covalent character of a certain percentage. There are none, in a theoretical sense, there are no bonds that are purely ionic. I know we transfer electrons and we produce ions, that's true. But even with ionic bonds, you get some of that electron density, when they come close together, the electrostatic charge difference is enough where it sort of steals the electrons away from the negative ion for a short period of time. So you get kind of a covalent character, even though it's still an ionic bond. If I didn't mention before, this bonding, if you have ionic, what we would consider a complete ionic character like sodium chloride on this end, and a complete covalent character on this side like the diatomics, like dinitrogen, oxygen, one of those fluorine, chlorine, those diatomics, those would be purely covalent. You have a continuum in between. So I guess you could say we invent covalent versus ionic just so we can wrap our heads around what's going on. This is true. When we talk about ionic compounds, we're not really talking about discrete molecules. Right? I'm sure I mentioned this before. So when you have ions in the vicinity of one another, you could have other anions around them. But then each one of these has another cation around it. And this is two-dimensional, but it goes on in 3 dimensions. So when we write the compound, we're just balancing charges for the simplest whole number ratio of ions. So with sodium and chlorine, since there's one positive and one negative, the simplest is this. Right, that's it. But that's not what you really have. It's not a molecule. It's not a discrete unit. Like a water molecule would be a discrete unit, or a molecule of nitrogen or oxygen in the air that you breathe. Those are discrete molecules, and they're bound together covalently. That is, they share electrons. More review. Ionic compounds are solids at room temperature. I don't know of any ionic compounds that are not solid at room temperature. And they have high melting points also, very high melting points. They tend to, not all of them, but they tend to go into aqueous solution fairly well. Sodium chloride, of course, is easily dissolved, but there are some ionic compounds that just don't want to go into solution. And we say that they precipitate. When you put the ions in there separately, then they bond together and they will no longer stay in solution. They just drop out as a solid. But a great many ionic solids do dissolve well in water. Conductivity, electrical conductivity. If your ionic compound goes into solution in water, it becomes conducting. That is, you have mobile ions that will conduct a charge between two electrodes immersed in the solution. For covalent compounds, though, they don't break up into ions. So, by and large, they don't conduct electricity. And if they do, it's very weakly conducting. There are some covalently bound compounds that do form ions if they're forced. So hopefully we'll get to those eventually. That's why this word usually is stuck in there. Covalent compounds that are soluble usually produce non-conducting aqueous solutions. Example, sugar. You can dissolve lots of sugar, table sugar, in water. In fact, you can put so much sugar in water, eventually you'll get more sugar than water in that solution. It's so soluble. But it'll never conduct electricity because it doesn't form ions. Okay. The covalent bond is, as I've mentioned before, is a sharing of electrons. And I think we discussed this earlier. When an atom wants to give up electrons or accept electrons, it's trying to look like a noble gas. Right? It's trying to complete that outer shell some way. If it's over on this side, the metals, the simplest way to look like a noble gas is to get rid of your electrons. Because you only got one or two of them out there. It's a lot easier just to throw them off and then back up to the next level, electronic level, and now you look like a noble gas. If you're over on the other side, it's energetically speaking, it's easier to acquire electrons. And then you look like the noble gas that's to the right of it, like chlorine. If it gets one electron, now electronically it looks like argon. That's what they're aiming for when they form bonds. Now, that discussion in terms of ionic bonds means that they acquire an electron wholly, completely. It's theirs. But for covalent bonds, it's like shared custody. You know, they're divorced, but not really. They're sharing electrons. And by sharing electrons, to anthropomorphize, the atom thinks it has a complete outer shell. So we're going to look at some examples here in a second. Hydrogen is the very simplest example. And if you look at the electronic structure of hydrogen, remember it's only got one proton and one electron. So the Lewis structure would be like that. Or if we wrote the electronic structure, it'd just be 1s1. That's it. Hydrogen's really simple to deal with at this stage. And if you get two of them together, like that, we don't need that right now, then it's got the same electronic structure. And if they share electrons, now, by forming that bond, this hydrogen thinks it has two, and this hydrogen thinks it has two. Now, we know they don't. But energetically speaking, they're close enough together that those outer orbitals share often enough to make it worthwhile. Right? So they appear to themselves, look in the mirror, they appear to themselves to look like helium, like with 2 electrons in the outer shell, and it's complete. At this s orbitals, 2 electrons, all you need, and it's full. And in that case, hydrogen looks like helium. And this would be a representation of the electron density. The probability of finding electrons around the hydrogen atom, when they come together and form the bond, then most of the electron density is between the hydrogens. But there's always probability that they'll occupy some space out here also. Remember, at this level, we can't say exactly where the electrons are. We have to speak in probabilities. They're more likely to be in this region between. Okay. Okay, so that's how we represent a shared pair of electrons. We would write it, of course, now we would write it like this. And that's a hydrogen, a diatomic hydrogen molecule. Or if we use even shorter shorthand, we just put a dash. And the dash means 2 electrons. Anytime you see a dash between 2 atoms as a bond, representing a bond, it's always 2 electrons. So if you need 2 more electrons in that bond, you got to draw another dash. So in the case of oxygen, we'd have 2. In the case of nitrogen, we'd have 3. Okay, so that just means that one nitrogen has contributed 3 electrons and the other nitrogen's contributed 3 electrons. And now you have 2, 4, 6 electrons between. Okay, now there are other electrons out here, but I just didn't draw them in. And we'll talk about those in a few minutes. Okay. Let's see. Oh, by the way, the sharing occurs between the sharing of electrons is only the valence electrons, those in the outermost energy shell. Right? The inner electrons, the core electrons, never participate in bonding. So that being said, we need to find out how many valence electrons are available for each of the atoms if we're going to see if they bond. For hydrogen, right, that's it. And there are no other electrons around there, Lewis dot structure. But with fluorine, remember fluorine has how many valence electrons? Count from the left. 1, 2, 3, 4, 5, 6, 7. Fluorine has 7 valence electrons. So we would draw it like this. That's 4 of them. 5, 6, 7. Actually, it'd be better if I do it like that. If I'm going to pair up with a hydrogen, it's got 1. So now they can form a bond by sharing those 2 electrons. And if we represent those 2 electrons as a dash, that's what you get. Now 2 fluorines can bond too, also. Or you can get 2 halogens bonded together. Bromine and fluorine, they have the same number of valence electrons. Right? They're in the same family. Bromine and chlorine, or bromine and fluorine can bond by sharing electrons. Look at them first. All right, those are bonding electrons. When they're between the atoms and they've paired up and we can represent them by a dash, those are bonding electrons. All the yellow electrons around the individual atoms are non-bonding electrons. So there are no non-bonding electrons around this molecule. And around this molecule, you have 6 non-bonding electrons. Around this molecule, you have 12 non-bonding electrons. And same here. They represent them in blue here. Sometimes they're called lone pairs. And when you have non-bonding electrons around an atom that's participating in a covalent bond, we try to pair them up. And most of them, the vast majority of bonding situations in the covalent description, all the non-bonding electrons will be paired. If you have an unpaired electron, but you still have that bond, then that's what we call a free radical. Any type of molecule or atom, for that matter, that has an unpaired electron is a free radical. And I'm sure you've heard of those in the popular media. Free radicals are bad. They're very reactive. So, and your body's producing them all the time. Just as a consequence of the biochemical reactions, your body produces lots of free radicals, and the systems in your body are designed to scavenge those free radicals before they do damage. So they get anywhere near your DNA, then they can do some serious damage. And that's part of the problem with UV exposure in your skin. That produces free radicals, and they damage cells. And at some point, they could damage a cell in a certain way, and it turns loose its inhibitions for growth and multiplication. And that's when you get cancer. Okay. What's the difference between bonding and non-bonding electrons? Bonding electrons are valence electrons that are shared. And the non-bonding are lone electron pairs that do not participate in bonding. But they're still valence electrons. They're both types are valence electrons. Okay, we're not even talking about core electrons right now. Okay, I mentioned earlier, 1 dash is a single bond, 2 electrons. This molecule, what would that be? Carbon dioxide. That's carbon dioxide. So you have a double bond on this side and a double bond on that side. So look at it this way. How many valence electrons does carbon have? 1, 2, 3, 4. Okay. How many electrons does it need to complete the outer shell? We're talking about right, the octet. So it needs 1 here, 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 here to complete the octet. So when you come in with an oxygen, which has 6, like that, 2, 4, 6. Now you can get a bond here and a bond here. Oxygen's full, it's not going to bond anymore. So you bring in another oxygen over here. Now you got a bond there. Oops. Let me redraw that. There we go. You got a bond there, and you got a bond there. Now that's not physically what happens, right? This is just a representation. So that's why you have a double bond on this side and a double bond on that side. Oxygen satisfied here, oxygen satisfied there, carbon satisfied here. Everybody thinks they're a noble gas. Nitrogen, on the other hand, needs 3. Dinitrogen, that is, needs 3. So what's the Lewis dot structure for nitrogen? Well, it's 5 over, right? So it's got 5 valence electrons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's got those two, those two, those two. 3 bonds. Now, if you count them up, 2, 4, 6, 8. It thinks it's got an octet. 2, 4, 6, 8. Thinks it's got an octet simply by sharing electrons. All right. How many electrons are shared in a double bond? Right, 4, right? 2 times 2 is 4. It is in my universe. Okay. Non-metal covalent bonds form between nonmetals. When we're talking about pure covalent or even majority covalent bonds, they form between nonmetals. And the concept here is, let's see, are we going to talk about, I don't want to introduce a topic that now that we're going to talk about later. It's called electronegativity. No, not that chapter, but this chapter. Yeah, okay, we are going to get to that chapter. Let me go okay. Maybe I do need to introduce that concept. We don't have to hammer the concept of electronegativity too hard, but a basic understanding of what it means helps understand what's going on here. Electronegativity is a way of quantifying the attraction that an atom has for electrons. The higher the electronegativity number, the stronger the pull. And as a general trend in the periodic table, electronegativity increases from lower left to upper right. So if you go up, you're increasing electronegativity. If you go to the right, you're increasing electronegativity. So that means fluorine is the most electronegative atom in the periodic table. It has a very strong attraction. And if you combine it with any metallic element, you're going to get a violent reaction because it's going to town with those electrons. It's just dragging them away. And the reaction is extremely exothermic. But if you try to combine nonmetals, all right, everybody up in this upper right-hand corner, they have pretty high electronegativities. They're dragging electrons to themselves. Well, if you try to put two of them together, what's the advantage there? The only option they have is to share. If they don't share, then there's no bond because nobody's going to give up all their electrons, their valence electrons, to the other one. So sharing is the only option you have if you're trying to bond non-metal to non-metal. Now, we do have metal-metal bonds. We're not going to talk about those here. I don't think. If we do, it'll be later. We're going to focus on non-metal, non-metal. And that's what we're talking about here. They have a strong tendency to form those covalent bonds because they have high electronegativity and they're not going to give them up. They'll share them for a microsecond, but they're not going to completely divest themselves of their valence electrons. And we've already seen an example of this statement. The number of bonds formed is equal to the number of electrons. The non-metallic atom must share to obtain an octet. Like carbon had 4, it needed 4. So it's going to form 4 bonds. Oxygen only needed 2 electrons. So it's going to form 2 covalent bonds. That's why carbon needed 2 of them. Now, is anybody thinking what I'm thinking? How do you get carbon monoxide? Okay, that's a little beyond us right now. Let's stick with the easy stuff for now. Okay. Just recognize that carbon monoxide does exist. So that means eventually we got to explain it. Right? Nature just does what it does. It's our job to wrap our brains around it and explain it. So carbon dioxide and carbon monoxide, they both exist. All kinds of oxides of nitrogen exist. N2O, NO, NO2, NO3. I mean, that make your head spin. Okay. So in this case, oxygen having 6 valence electrons needs 2 electrons to complete the octet. So it can do that 2 different ways. It can either make 2 single bonds or it can make 1 double bond. Right? 1 double bond with another oxygen would do it. Or go halvesies with another oxygen on carbon, that would do it. Or oxygen can form single bonds with another element that only needs 1 electron. So the prime example of that is water. Right? Oxygen and hydrogen. So there's 2, 4, 6, 8. So oxygen now thinks it has an octet, and hydrogen thinks it has a duet. That's all it needs. 2, 4, 6, 8. Now we're going to look at, hopefully, if I don't talk too long, we're going to look at why the structure is like that. Now, why is it bent? Why isn't it just hydrogen, oxygen, hydrogen, straight across? Okay, we're going to look at that later. I hope I get there. Nitrogen needs to form 3 bonds, and it has 3 options. Right? It can form 3 single bonds. It can form a single and a double, or it can form 1 triple bond. And it's perfectly happy to do that. We mentioned carbon earlier. This is probably why organic chemists can make a living on just the behavior of 1 element, carbon, because it can form 4 different bonds, types of bonds. 4 singles, 2 singles and a double, 2 doubles, or a single and a triple. Now, why don't we have a quadruple bond in there? In order to do that, you need another atom that also needed 4 electrons. Right? So maybe you could do that with a carbon. I bet somebody's tried. I just don't know of an example. I haven't heard of that compound being formed. Now this one, 4 single bonds, right? That's the one that holds the girl's best friend together, the diamond. And it forms a tetrahedron. We'll talk about that later also. Okay, how many covalent bonds can oxygen form? 2, it only needs 2 electrons. So it can form 2 bonds. Now, there's a special kind of covalent bond. Up to this point, we've been talking about sharing, like 1 electron from this atom and 1 from that one come together and make a bond. Okay? But there are occasions when a covalent bond is formed and both electrons come from 1 atom to form the bond. That's called a coordinate covalent bond. A special kind. And the interesting thing about it is, once the bond is formed, you can't say how it was formed, right? Because it looks like any other covalent bond. 2 electrons in the bond, right? Where did they come from? I don't know. Unless you know the circumstances before the bond was formed, then you can deduce that it was a coordinate covalent. But after the bond's formed, there's no way to tell. It looks like any other covalent bond. And this happens when one of the atoms needs 2 electrons to complete its octet, but it doesn't have any to share. So it takes the 2 electrons from the other atom, and now it's complete, and the other atom already had an octet, but now it's still got an octet. So it's kind of a weird symbiosis, I guess, in a sense. Example, HOCl, right? Notice that hydrogen has its duet, oxygen's got an octet, chlorine's got an octet. So HOCl is perfectly happy, just like it is. What would that be? Remember the polyatomics that we had like this? Started off with that one, and then we take away an oxygen, and we take away another oxygen, right? And then we add an oxygen here, right? So this is chlorate, chloride, hypochlorite. Just added hydrogen, right? If you put it in water, that would be hypochlorous acid. So there's your HOCl right there. And it looks like, well, that's the electronic structure for it. Yep. But it will also form another bond with another oxygen and make this compound with hydrogen, right? It'll do that. But it's already happy like this. So in order to do that one, this oxygen, which has 6 valence electrons, it needs 2 more, right? And instead of getting 2 from another atom that has 2 to share to make its octet, it just takes these 2 from that one and completes its octet. But since it's sharing with this molecule, it's still got its octet. It didn't lose anything by forming that bond. Okay, that's a coordinate covalent bond that was formed here. But after you reach this point, there's no way to tell. Right? The only way you know it's coordinate is if you assume that we made it this way to do that. Okay. All right. This comes out of your book, and I don't think it adds to the discussion very much. I probably ought to just take this slide out. It just compares the regular covalent bond to a coordinate covalent bond. It's just the source of the electrons makes the difference. That's it. And this says the same thing I've said before. There's other examples right here. Nitrous oxide. In this case, we form a single bond here. Think of it in these terms. Dinitrogen is perfectly happy. I mean, we breathe it in all day long. Breathe it in, breathe it out. Microorganisms actually use it. They make food out of it. But if oxygen binds to this, it's got to take 2 electrons from that nitrogen to make the bond, right? So that's definitely coordinate covalent. Carbon monoxide. Okay, here, they're going to answer my questions. Carbon monoxide forms 3 bonds instead of 2. So how does it do that? Well, let's look at it. If we say carbon has like that, and oxygen is like 1, 2, 3, 4, 5, 5, 6. That two, 4, 6, 8. Okay, that's 2, 4, 6, 8. It forms 3 bonds. How's it going to do that? Well, we got these 2 here. We got these 2 here. Oxygen's happy. So what is it going to do? Well, if we take these 2 and put them over here, now we got the 3rd bond. So that's a coordinate covalent bond that formed with these two electrons coming completely from carbon. So actually, oxygen, there's no advantage for oxygen, but there is an advantage for carbon to do that. Now it has an octet. Okay. So I think we beat that horse long enough. Steps for writing a Lewis structure. We introduced some of this discussion last time, but there's a way to do this, so you can do it for very large molecules and draw the structure. What you have to do is be presented with a valid compound, like SO2 in this case. Or you could do it with actually you can do it with polyatomic ion. Polyatomic ions are covalently bound groups that have an electric charge distributed over the entire group. That's why they go through reactions as whole units lots of times, because they're so strongly bound together. SO2, we could do that with SO4, 2 minus. Okay, so I'm going to use this example, even though that one's probably easier. But what you do is you count up the valence electrons for each of the atoms, plus any excess charges that you have. In this case, you don't have a charge, right? So you just count up the valence for each one. Sulfur is in oxygen's group, so it has 6 valence electrons. 6 there. Oxygen also has 6, but it's times 4, so it has 24. And then we plus 6, it has 30, and then plus 2, because each one of these represents an electron. Plus 2 is 32. So this group, this sulfate polyatomic ion, has 32 valence electrons that we have to distribute in a Lewis dot structure. Okay? Did I lose anybody? I was just counting up valence electrons, right? Oxygen, actually oxygen and sulfur are in the same group, so we could just say, all right, 6, we have 4, 5 of them. 5 times 6 is 30, plus 2 is 32. Okay? That's the first step. Count up all your valence electrons. Then you hook the atoms together with a single bond. But you need to know which one is in the center. And the one in the center is the one that is least electronegative. So in this case, sulfur is below oxygen. Remember I said from lower left to upper right. So as you go up the group, you get more electronegative. So we put the sulfur in the middle and the oxygen's around it. In fact, that's the only way that makes sense, because there's only one sulfur and we've got to distribute these oxygens. So for our sulfate, which has 32 valence electrons, we have a sulfur, and then we're going to form a single bond with all of the oxygens. Okay, they're using dots, but I'm just going to go ahead and use lines, dashes. So that's 2, 4, 6, 8, right? Minus 8. We've used up 8 of them. So that's 24 electrons that we have left. Okay. Now you start from the outside and work your way in, placing your electrons. 1, 2, 3, 4, 5. Oops. Unpaired first. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, we've used them all up. Okay. All right. So now that we've positioned all of our electrons and we look to see, do they all have octets? Right? 2, 4, 6, 8 around sulfur. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. Right? If they didn't, we'd have to do something to make the octet. We might have to form a double bond. We might have to, that's most commonly the way you do it. In this case, that's the Lewis dot structure of sulfur dioxide. Now, why are they doing that? Hold on a second. Oh, in this case, here we have an octet around sulfur. There, we've only got 6 electrons. See, 2, 4, 6. When we do that same procedure for that one as we did for this one, we only get 6 electrons around the sulfur. So now we have to deal with, we need to put 8 electrons around sulfur without depriving oxygen of its octet. So the easiest way to do that is take 2 of these electrons and put them right here between. You can't move them over here because then oxygen is depleted. So if you move them into a bond, now they're sharing. And that's what this next slide does. We take 2 of those and put them over here into a double bond. So now we have a single bond on that side and a double bond on that side. Okay? So that's what we call a valid Lewis dot structure. But that's not the only one. There could be others. Right? What if, instead of these pair, we had taken the pair from this side and put it over here? Okay. So those bonds are not equivalent because they're on opposite sides of the sulfur. So how do you deal with that? Well, let's see. I might as well introduce the concept now. We'll get it later. When you have to do that, and you can write more than one valid Lewis dot structure, and the structures are equivalent, like these two, to be that one versus the other one. So we have oxygen, single bond, sulfur, double bond, oxygen, and then like that. Let's see, 2, 4, 6, 8. Yeah. And then 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. If we wrote the other one like this, okay, then what you have to do with this arrangement is you have to say, okay, I can't choose. I want both. So you say, in reality, what happens is they just shuttle back and forth. So it's something in between. And this is called resonance. These are resonance structures. So that's what we have to do. And the reason we have to do that is because we painted ourselves into a corner. By using this methodology, there are limitations, and this is one of the limitations. You can write more than one valid Lewis dot structure for lots of molecules. And the only way to explain it within the confines of this theory is with that invention. Remember early on when I talked about what do you do when a theory doesn't work? You either got to throw it out, start over. You got to modify it to accommodate, right? Which is what we've done here. Or, what's the other one? Let's see, throw it out, modify it, or, that's gone blank. Let's see. Modify the theory. Oh, I just remembered. Restrict its use. I'd say, We could say, no, you can't use it there. Won't work, can't use it. Problem is that there's so many of these examples, it would restrict the use of this part of the theory to where it's almost worthless. So then you'd be closer to throwing it out. So we say, okay, we're going to modify it. We're going to say, all right, here's what we're going to do. We're going to say resonance. And that solves the problem. At least until some other fly in the ointment is found. Eventually, we have to throw this out altogether anyway. But for many certain instances of bonding, this works great. And it helps explain how bonds are formed and how molecules behave. So it's worth keeping. At some point, we keep modifying it, and then we reach a point where, okay, now we have to restrict it. We can't use it in some circumstances. All right. So examples, right? That's an easy one. That's an easy one. That's an easy one. Those are Lewis dot structures. And you would, technically, you would start with the same thing, count the valence electrons, form a bond, and then place the rest of your electrons around, starting from the outside and work your way in. Okay, there's ammonia. Right. So you'll notice that you got duets here and you got an octet there. Nitrogen's in the middle. Whenever you have hydrogen, hydrogen is going to be out here somewhere. Simply because you can only form one bond with hydrogen. You try to put hydrogen in the middle, you won't get any bonds. Right? It'd just be that one bond and there's nothing on the other side. So hydrogens always go to the outside. Okay, carbon dioxide we've looked at before. Carbon tetrachloride. So all you have to check, if you count up the valence electrons and then you count up all the electrons plus the bonding ones, you'll find that they're equal in number. That verifies that this is a Lewis dot structure that's valid, plus the octets are there. All right. Total number of dots in the Lewis structure for SO2. It should be equal to the total of the valence electrons. Excuse me. It depends on what their interpretation is. If they're saying the dots include those that are in the bonding, yes, that's true. But if you draw the little lines, then you could say, all right, technically, some of those are tied up in those bonds. But then what they would have to say is how many lone pair electrons are there? Non-bonding electrons. That would be a valid question. And then you would subtract the bonding from the total. Okay, polyatomic ions. I mentioned these earlier. Polyatomics form ionic bonds with other compounds, with other ions. But within the polyatomic, all the bonds are covalent. So you sort of have a mixture. Here's an example. Potassium sulfate, right? These are the ionic bonds, but the covalent bonds are inside here. That's a correct structure. This is not a correct structure. So when you're doing a Lewis dot structure for an ionic compound, you have to transfer electrons completely. And then you may also have a covalent structure built into it. So this is a mixture. This is not valid because these are not covalent bonds. Those are ions. This is an ion. That's the correct structure. Let's see. We counted those up earlier, didn't we? 32. Don't forget to add the charge in there. Those two electrons that are forming that charge are spread over the entire molecule. They're somewhere in there. Well, actually, they are in there somewhere. It's just that the balance of charge is in favor of 2 extra electrons. But every electron is accounted for here. All right. Molecular geometry. What are we talking about? Well, it's a special kind of geometry. It's like, what's the spatial orientation of everything in the molecule? What does it look like in 3 dimensions? We've gone beyond plane geometry, right? Parallelograms, triangles, circles, things like that. Now we're in 3 dimensions, right? Where you have maybe a cube or a sphere. We have to think in 3 dimensions when we're looking at molecules. And they have a significant impact on both the physical properties of compounds and their chemical behavior. And I hope by the end of this discussion that will become clear. So what do? We learned the Lewis dot structure for a reason, because the Lewis dot structure feeds into this theory, VSEPR. That's an acronym for valence shell electron pair repulsion. That's a mouthful, I know. But all it means is when you position atoms around a central atom, they're going to push away from each other to the maximum extent possible. They want to minimize repulsion. So if you try to push them close together, right, all these electrons are going to push away from each other. So there's a happy medium in there. And that's what we're looking for with the valence shell electron pair repulsion. Minimize the repulsions. Now these electron pairs, they can be lone pairs, and they can be bonding pairs. They're treated the same way for deriving 3-dimensional structures. And the starting point is the Lewis dot structure. Draw the Lewis dot structure first, and then you look at what does that give you. And I'm going to explain that right now. We look in terms of groups, actually. I know the name says valence shell electron pair, but it should say electron group repulsion. And the reason I say that is we treat double bonds, single bonds, triple bonds the same. If you got one of these, that's a group. One of these, that's a group. That's a group for counting purposes. So if you have carbon tetrachloride, how many groups are around carbon? 1, 2, 3, 4. 4 groups. No lone pairs. If there were lone pairs, we count them up. For instance, ammonia. Right? We saw that one earlier. It has a lone pair here. So how many electron groups are there? 1, 2, 3, 4. Okay, that's how you count them. If we had, let's see, what was that other one? Hydrogen, chlorine, oxygen, and we had 2, 4, 6, 8, and 2, 4, 6, 8, before we added the other oxygen, right? Hypochlorous acid. So how many groups would be around the chlorine? 1, 2, 3. We count the doubles as one group. Around the oxygen, there would be 1, 2, 3. And around the hydrogens, just 1. Okay, for counting purposes. All right. So now that we know how to count electron groups, what do we do with them? Well, this goes through the steps. Like I said, you draw the Lewis dot structure first. Then you determine the number of groups of electrons, both bonding and non-bonding. Right? And add them up. How many are there around the central atom? We're going to keep it simple. We're going to have a central atom and then what we call ligands sticking out from it. This can also work for larger molecules. And the structure is based upon a central atom, anywhere you want to pick it. So if you've got a structure with lots of atoms here with different numbers of groups around that one, then this one, then that one's going to have a different geometric arrangement around that atom than this one does. But we're going to keep it simple first, like ammonia, just one central atom and then the groups around it. Okay, so once you've determined the number of electron groups, then it feeds into standard geometric shapes. Okay, if you have two groups, let's do it like this. I'm not even going to put one group because one group is always linear. Two groups. If you have two groups around the central atom, and that's all there is, it will be linear in geometric shape. So this is what we call the electronic geometry. So if there are two groups, it's linear. Example. Carbon dioxide. Right? Around the central atom, you have one here and one here. Now, you have lone pairs here and here and here, right? To complete the octet. But we're focusing on the central atom. One group here, one group there. So what's the geometry around that central atom? It's linear. That's the maximum, the best position for those electron groups for repulsion purposes. If you try to push this one around that side, then you minimize repulsion on this side, but you're increasing it on that side. So if you have two groups, linear is your ticket. If you have three, you have what we call trigonal, like triangle, planar. That is, for example, so maybe they've got some examples here for me. Well, there's linear. Two electron groups, three. Oh, water. Duh. Water's got, no, that's not water. That's formaldehyde, excuse me. Water doesn't work, formaldehyde does work. Okay, so formaldehyde has this arrangement. Okay. With its lone pairs here and here and here. But around that central atom, you get 1, 2, 3 groups. 2, 4, 6, 8. It's got an octet, but there are only 3 groups. So its ideal arrangement is trigonal planar. That is, minimizing repulsion means that everything's in the same plane. You don't try to bend one of these out here because that puts it closer to the other two. And they're pointing toward the apex of an equilateral triangle. Angles. So what's the bond angle here? Right, around that, 180 degrees. Because on the other side is 180, and all the way around is 360, right? All the way around here is 360. So what would each one of these angles be? 120, right? 3 times 120 is 360. So this angle, that angle, that angle, they would all be 120 degrees. Okay? You're scratching your head from geometry days. Everybody had geometry here, don't you? Okay, good. If you have 4 bonding pairs, then what's the most efficient arrangement of those 4? A tetrahedron. a tetrahedron, and methane is the best example here, or carbon tetrachloride, that would work. So if you have carbon and 3 chlorides around it, you have like that. There's a chlorine here. There's a chlorine there, and then there's one in the back. And that forms a triangle base. Plus, like that. So that arrangement, that tetrahedral arrangement, is the most efficient distribution of those 4 around that carbon. 2, 4, 6, 8. Now, the shape, the edges of those regular shapes, like this triangle, those are not bonds. Those define the shape of the molecule. The trigonal planar defines the shape, not the bonds. The bonds are still between the atoms, right here, here, there, and there. Okay? So don't get those confused, if you can help it. So that's the tetrahedron. And that's the arrangement of carbon atoms in a diamond, tetrahedron. All right, that should be the next one. Yeah, here's methane, CH4. These are all electronic geometries, which means we're including everything. Lone pairs, we haven't had lone pairs here or here. We did have, no, we haven't had any lone pairs yet. But if you have lone pairs, like ammonia, right? Here we go, ammonia. You got 1, 2, 3, 4 groups because there's a lone pair in it. So the electronic structure is tetrahedral. So where does this lone pair go? Well, this would be nitrogen, hydrogen, 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 and that lone pair would go up here. So it has 4 groups and gives you the tetrahedron. Water's the same way. Around oxygen, you've got 2 hydrogens forming bonds, but you've also got 2 lone pairs. So there'd be a lone pair here and a lone pair here, and a hydrogen and a hydrogen. Okay? Okay?
Yeah, I'm fine, I'm sorry.
Okay. If you think about it too hard, I guess it could give you a headache. Now, I'm told when we start talking about shapes and geometries and stuff, that women do better with than men do, because men are more linear and left-brained. So it takes a lot of work, and it's taken a lot of work for me to wrap my mind around this stuff. And if you're going into organic chemistry, this is everything in organic chemistry, shapes. All right, so I would expect women to do really well as a general rule. But we're not done yet, because there are other geometric shapes, and you can have more atoms packed around there. Let's see, how are we doing on time? Am I eating up my time?
It's 10:17.
Okay, and we're supposed to quit when?
I think 11.
Okay. So I better move on. Okay, we're not going to go beyond that. If we need, I'll go on. You can go 5 groups, you can go 6 groups. I always stop at 6 groups. But you see where I'm headed with these shapes. Now, if you do have lone pairs, like oxygen, water. Water would be like this, and you'd have 2 lone pairs up here. That's the Lewis dot structure. Since you have 4 groups, that would be in a tetrahedron. But notice, with a tetrahedron, if we put a lone pair up here and here, then if you disregard the lone pairs, you're actually now talking about the molecular geometry. If you disregard the lone pairs, the molecular geometry now is bent. Because in reality, you don't see those lone pairs. Right? You just see the atoms and they're bonded. So, oh, I didn't talk about the bonding angle here. The bonding angle is, hold on a second. I can't remember what it is. It's an odd number. Hopefully we'll get to it. Or it'll come to me when I least expect it. Okay, so when you have an atom with more than one central atom, they're making the point here that I did earlier, you'll have geometries around that central atom in the larger molecules. In this case, they're both the same, right? You look around there, you got two groups. That one's linear, that one's linear. This one's got 4, so it's tetrahedral around that one, and it's also tetrahedral around that one, hydrogen peroxide. Okay, but if you disregard these lone pairs, you got it's bent right there, and it's bent right there. Right, no bends here. What's that one? That's acetylene. There's your hydrogen peroxide. Right, it's bent here. It's bent there. This one is hydrazine, I think. That's hydrazine. And it's linear around this one, and it's bent around that one. It's got 1, 2, 3. So what is this electronic structure? Trigonal planar. But if you cover up that part of the triangle, now you've got just that bent part left over. Okay, I pulled these are not in your textbook. I pulled these out as, so if you have a linear arrangement around that central atom, if you have 2 groups, it's linear. There's your trigonal planar with 3, tetrahedral with 4. If you have 5, then the best arrangement is trigonal bipyramidal, which means that you've got a trigonal base pyramid, which is basically a tetrahedron. But if you put 2 of those butt to butt, then you get your tetrahedron down here. Well, actually, you don't get a tetrahedron because it's got a trigonal base in the middle and then the 2 apexes here. So this trigonal bipyramidal is for 5 electron groups. And 6 electron groups is a square base here, and that's called an octahedron. Octahedron means 8, so it's got 8 sides. If you count them up, right, there's 1, 2, 3, 4 on that, 1, 2, 3, 4 there. So we got 8 sides. How many sides we got on this one? 1, 2, 3, 1, 2, 3, 6 sides on that one. Okay, and then what this does is it emphasizes the point of the difference between electronic geometry, that's what I'm calling it, and molecular geometry. So if you, let's see, if you have this one, this would be ammonia, nitrogen and 3 hydrogens in a lone pair. What you would have is a trigonal pyramid. You'd have a trigonal base with nitrogen at the apex. That's the molecular geometry. So you have to go through steps. You have to do the Lewis dot structure. You have to define the electronic geometry and then disregard the lone pairs to find the molecular geometry. The molecular geometry is important because that determines the polarity of the molecule and how it interacts with other molecules when they smash into each other. Okay. Let's see. Let me check my hard copy and see, because I don't want to miss. Okay, we're going to talk about polarity here also. All right. So let's not spend a lot of time here. Wait a minute. Trigonal pyramid bend. No, it doesn't have it. I'm looking for that tetrahedral angle. I want to say something, but I'm not sure it's right, so I'm not going to say it. So what theory is used to predict the geometry? Valence shell electron pair repulsion theory. That's it right there. Electronegativity. Okay, we are going to talk about it. So I don't have to spend a lot of time because I've already explained this one. It's just the ability of an atom in a molecule to attract shared electrons to itself. That's how it's measured. So in order to make that measurement, you have to get the atom in a molecule. And then you measure the difference between where the electrons spend their time. And there are ways to measure that. We don't have time to discuss them right now. And this tells you the relationship, lower left to upper right in the periodic table. So what we're doing is we're actually learning ways to use the periodic table, more ways to use it. It's arranged this way for a reason. Lower left to upper right means increasing electronegativity. And that's, okay. These numbers, there are several ways to determine electronegativity quantitatively, but this is the most common one, developed by Linus Pauling. Electronegativity values. And notice fluorine has the highest one. And then you decrease from here down to here. Now, why did they leave out this section in here? These guys right here, the transition metals. Well, they sort of do this thing. They make a hump and then they come back up. So we leave those out for general discussion. But they do have electronegativities. It's just that they're not as well behaved as the representative elements, those in the first two columns and the last six. Let's see, 1, 2, 3, 4, 5. Well, okay, we don't include the noble gases. They've got all the electrons they need, and it's difficult to form compounds with them anyway. So by definition, it's hard to measure. Okay. Let's see. If lithium and fluorine react, which element will have more attraction for an electron? Now, lithium and fluorine, that's a metal and a nonmetal. This is going to be an ionic bond, but you can still speak in terms of which one attracts electrons more. And since lithium is on the far left, fluorine's on the far right, fluorine is going to be a stronger attractor for electrons, right? How about fluorine and iodine? Right, fluorine's up here and iodine's there. Fluorine's going to be a stronger attractor. Okay. Highest electronegativity in this group. Well, let's see. We look where we're located. It's difficult to say. Really, helium won't have an attraction. Hydrogen's on the far left. Oxygen and chlorine, how are they related? Well, let's see. It's a little difficult because oxygen's higher, but chlorine's further to the right. Right? So how do we figure that one out? Sometimes you don't. You can speculate, but really it boils right down to making the measurements. And it turns out oxygen is more electronegative than chlorine. Not by much, just by a hair. Okay, so when we get two atoms bonded together, what happens is the electrons tend to spend more time around the electronegative atom than the non. The more electronegative atom will tend to attract electrons to itself. So the bond between two, like this one, the electrons are going to spend more time over here. So it'd be something like this. What that leads to is bond polarity. In other words, if the electrons spend more time over here, that's going to be the slightly negative side, and this is going to be the slightly positive side. That's what we mean by bond polarity. And we designate it with a special symbol. Draw an arrow showing the direction the electrons move. And then we say, that's the plus end. Now, this is not a complete charge. It's only a slight difference in charge. So we also may designate it like this. We use a Greek letter delta. And like that, right? If it were an ionic compound, you'd leave that out, just say negative. That implies a complete transfer of electrons. This just means a slight difference in charge. Now, when do we not have a polar bond? When both of the atoms are identical electronegativities, right? Dihydrogens, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all those diatomics, they will be non-polar bonds. Okay? If you get two atoms with different electronegativities, there's always the potential for a polar bond. Hydrogen chloride, right? It would be a polar bond. Which makes, since there's only one bond here, what does that say about the molecule? It says the molecule is also polar. If you have multiple bonds, then you have to consider not just the polarity of the bonds, but geometry. If you have, let's see, are we going to get an example here? I'm not going to show us an example. Back up. An example of, let's see, water. Right? We know the shape of water is going to be bent like that. Okay? Which way is the polarity? Well, oxygen's far to the right. So it's going to be toward the oxygen for each of these bonds. Okay? Plus we have these lone pairs out here that add electron density to that side of the molecule. So that's also considered. So what would happen if we had hydrogens positioned like that? They would cancel one another out and make a non-polar molecule. But since they're bent, we do what we call vector summation. It's not a direct A plus B. It takes into account direction as well. That's why we say vector. So when we add these two together, we get an overall polarity of the molecule in that direction because of the shape. If it were linear, then they would cancel one another out. Right? They'd both be opposite one another. But since they're bent, now we get a vector summation that's going in that direction. What about carbon dioxide? I'm going to leave out the lone pairs for argument's sake. Like that, and like that. Because oxygen is more electronegative than carbon. It's to the right of carbon. But notice it's a linear molecule. So these things cancel one another out. That makes carbon dioxide non-polar. Okay. So when you're looking for polarity or non-polarity in a molecule, you look at two things: the polarity of the bonds and the geometry. Okay. Now, what do we call polar and what do we call non-polar? Remember, I mentioned continuum. There's a continuum in polarity as well. If the electronegativity difference between the atoms, then now we're just talking about individual bonds, right? For simplicity's sake. The individual polarity between the atoms, you subtract the lower from the greater, and you say, how big is that number? If the number is less than 0.4, the difference between them, we say that's a nonpolar covalent bond. If it's between 0.4 and 2, then we're in the covalent range. But there's a dividing line in there also, 1.5. If the difference between the numbers, those Pauling numbers, is 1.5, between 0.4 and 1.5, we say we have a polar covalent bond. If it's between 1.5 and 2, then we say it's kind of a gray area. It depends. It could be polar covalent, it could be ionic. And in that case, we look to see, is there a metal involved? If there's a metal involved, yeah, it's definitely ionic. If it's a nonmetal, we say we're still polar covalent. Okay. But if the difference is greater than 2, doesn't matter what the atoms are. If it's greater than 2, it's ionic. Okay. So that's the, I guess you could say it's the arbitrary system. 0.4, 1.5, and 2 are the dividing lines. Okay. Arrange the following bonds in descending order of polarity. So most polar to least polar. Well, notice that they're all bound to fluorine. So all we need to do is say, how far away are they from fluorine in the table? Right? Which one's the farthest away? Let's see, nitrogen, oxygen, carbon. Nitrogen, oxygen, carbon. Okay, carbon, fluorine will be the least polar, descending order. So the most polar, carbon, fluorine, okay, carbon, fluorine would be the least polar, and the most polar would be, oh, excuse me, no, oxygen, fluorine would be least polar. They're closer together. Carbon would be the greatest. And then in the middle would be nitrogen. Right? Carbon, nitrogen, oxygen. Now we're getting into different pairs. So we look at the distance between the two. Which one's the farthest apart? Let's see. Carbon, fluorine is pretty far apart. Nitrogen, oxygen is close together. Silicon, fluorine is pretty far apart. I say silicon, fluorine would be the most polar. And then the next would be carbon, fluorine. And then nitrogen, oxygen. Okay. This is a nonpolar bond because those atoms are equal in electronegativity. Boron and chlorine, look how far apart they are. Sulfur and chlorine, they're closer together. So this would be the least polar, this would be next, and this would be the most polar. So we have boron, sulfur, and chlorine. Okay, that's sort of a, not even semi-quantitative, that's a qualitative assessment of polarity by comparison. So when you're presented with a question like this, which is the least polar yet considered covalent? So to do this, we'd say, we would throw out the ones where nonmetals are involved, like throw that one out. This one would be questionable also, but actually it's easy. Least polar yet still considered polar covalent. Okay, so it has to be polar. That means we've got to throw oxygen out also. So the least polar, we'd throw this one out, throw that one out, then we would look at these comparisons. That one, that one, that one. And the closest ones together, nitrogen, oxygen will probably be it. Oops, how'd that happen? There we go. I'm going to skip this most polar without being considered ionic. Okay, let's see. This talks about what I just mentioned. You look at the individual bond polarities and then the molecular geometry, and that defines the overall polarity of the molecule. There's carbon dioxide example. I used that one earlier. Here's water. And here's hydrogen cyanide. Notice that both of these arrows are pointing in the same direction. So that was, even though it's linear, they add up. So these are both polar molecules. Let's see. I don't want to run out of time, so let me move on. Binary moleculars. These are two non-metallic elements. We encountered those when we were naming compounds, type 3s, where you have two nonmetals together. These are binary molecular compounds. So that's nothing new. We've already learned how to name those already. Actually, did we talk about those? Yeah, we did type 1, 2, and 3. Yeah, okay. So is this redundant material?
Is that the non-metal metal?
Yeah,
That's in chapter 4.
okay. So this is repetition. You already know how to name non-metal nonmetals.
Yeah, we started on last week.
Yeah, two non-metallic elements together. Since you can't balance a charge like you would for a type 1 or a type 2, you have to say how many there are. And then you also have to say which one comes first. Well, the one that is least electronegative comes first. Right? So if you have nitrogen and oxygen together, you write this one first, this one second, because nitrogen is less electronegative. It's closer to the metallic side. So you say nitrogen monoxide. Just how many are there? Or if you had two, nitrogen dioxide. Or if you put the two over here, dinitrogen monoxide. But the first one is the one that's closer to metallic or lower electronegativity. Okay. So these are your prefixes, right? If I didn't talk about those before, you just have to memorize those. They're derived from the Greek: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Those are the only ones we're going to learn in this class, just up through 10. Didn't I talk about all three types already? Okay, I thought I did. I must have, because somebody's already turned in that extra credit. I've already got one of those.
So that's what chapter 4 was on.
Okay, okay.
When is that extra credit due? Before the next exam?
Uh-huh. Yeah. You can turn it in on exam day if you want. Unless you really want to stick those credits in there and boost your grade.
I'll probably go to you.
Build yourself up, yeah.
Yeah.
Okay, concept questions. We really don't have time for that right now. You just apply the rules, right? And if you need to go back and review your hard copies and the video that I'm going to post, you can go back and look at that and see how to, and work problems. Your homework problems will have examples. Okay. That's enough for now. Take a short break and we'll